All right, so we're going to start 2.3, deductive reasoning. Um, we have talked about inductive reasoning before, and today the focus is deductive. If you remember, inductive reasoning was where we looked at patterns to find um, an explanation of what might happen in the future. Deductive reasoning is a little bit different, and we'll talk about that here pretty soon. But to start, we've been talking about conditional statements. A conditional statement, now we're going to, mathematicians like to be efficient. So rather than writing all those words that we've been doing the past couple of days and you get a little bit frustrated, we can do something to write these statements faster. And so we have this symbolic notation where we're going to use P to represent the hypothesis. That's usually the first part that comes. Q to represent the conclusion. And now this arrow means implies. So if I wrote something like this, P implies Q. Okay, so P implies Q. If P happens, that implies that Q happens. Okay, so this would be a conditional statement like if P, then Q. So that's just a regular conditional statement. Now we also have some other tools. This tilde symbol, it's called a tilde on the keyboard, means negate. So if you see this symbol in front of a P, it means the negation of P. It's the not. So if you guys remember, I could write something like this. The not of P implies not Q. And what statement would that be? When you negate them, that would be the inverse. Okay, the inverse was where we negated it. So if P doesn't happen, then that implies that Q doesn't happen. So the converse now, the converse would be, I'll give you a little minute to try it. It's going to be where you flip the hypothesis and conclusion around. So if Q, then P. And we have one more left here. And that is the contrapositive. Okay, so the contrapositive is going to look like what? Okay, so the contrapositive was where we flipped the hypothesis and conclusion and negated it. It's both the inverse and the converse. So it starts off if the conclusion didn't happen, that implies that the hypothesis didn't happen. Okay, so these are something you might want to have down in your notes. It might make it easier to remember what the inverse is if you know the notation and you got it abbreviated quickly. So I think it'd be worthwhile to write down. The one symbol I did not talk about is this double arrow, and that is for biconditional statements. So if you wanted to use a if and only if statement, right? Biconditional means it works both ways. If and only if you use the double arrow, meaning it works both ways. Okay. So I got that stuff written again here, written out nice. And we can go on to example 1. Let P be the value of x of negative 4, and Q be the square of x is 16. So here they want us to write regular conditional statement in words. So how do I take the hypothesis, P, and the conclusion, the square root of x is 16. To write a conditional statement, well, conditional statement, most of the time we're going to write if something happens, then what happens. Okay, so if the value of x is -4, and then the square of x is 16. True statement, right? If the value of x is -4, then if you square x, you get 16. -4 times -4 is 16, positive. Here we have Q implies P. So we flip the hypothesis and conclusion. That is your converse. So we're going to write if, now we're going to start with the conclusion. If the square of x is 16, then the value of x is -4. Okay, so the conditional statement was true. How about the converse? Is the converse true? If the square of x is 16, then the value of x is -4. Hopefully you're saying, well, what about positive 4? If the square of x is 16, there could be two values to give you, when you squared them, gave you 16. So this would not necessarily be true. So if there's a counter example, x could have been 4, that means the statement is false. It's not always true. Decide whether the biconditional statement P is the P is if and only if Q is true. So if the converse wasn't true, is it going to work both ways? No, it's not, right? The converse is false, so you cannot write this as a biconditional statement. So it is not true, so we can say false. In this next example, we're going to move away from the actual math hypothesis and conclusions and just go with some everyday statements that you might make. So if conditional statement here, it's always good to know all your statements. You know, here they don't even ask for the conditional statement, but understand that it's going to be if today is Monday, then there is school. That's most of the time true. But now they want us to write the contrapositive of P implies Q. So P implies Q is the conditional statement. Contrapositive is where we flip and negate. So we're going to say if there is no school, then today is not Monday. So now to write the inverse of P implies Q. Okay, so it's nice to make sure you know these words because they don't always go in the order you expect to see them. And people will just kind of get them wrong that way. The inverse is where we negate the statement. So if today is not Monday, then there is no school. Alright, looks like I'm missing the line there. All right, let's keep going. Um, so the whole point of all this um, looking at conditional statements is because how our geometry book is set up with deductive reasoning, set up using deductive reasoning, and um, with that deductive reasoning, we have a lot of conditional statements. We have a lot of theorems that say, if this is true, then this is true. Okay, so it doesn't mean it's always true, but if the first part is true, then the second part is true. And we're going to go through and we're going to explain everything in our book by using this deductive reasoning. Okay, that deductive reasoning is using definitions, accepted properties in a logical order to make a logical argument. Okay, so we're all about logical in geometry class. Okay, some people like that part, they like the thought process, and some people haven't practiced it much, and it's a struggle at first. But if you know your definitions, you put the time in to study, it's not going to be a problem. Okay, but if you just rely on your notes and you don't know things from chapter 1 still, like angle bisector, you could be in trouble. Okay, so it's important that you take the time to really understand the concepts so that you can be logical about them. Okay, so um, the law of detachment and the law of syllogism are two laws um, that we can use with our conditional statements. So the law of detachment is kind of just a pretty basic one. We want to state it because if it wasn't true, we'd be in trouble and there'd be no point to making these logical arguments. Okay, so both of these hopefully kind of make sense that if your hypothesis is true, then that implies your conclusion is true. If that is a true statement, then if P is true, then Q is true. So um, if you think about those from example 2, if today is Monday, then we have school. So P is your hypothesis. If today is Monday, then we have school. Okay, so if P is true, then we have school. That's the law of detachment. It follows. If P is not true, say today is Tuesday. Well, if today is Tuesday, well, does it mean we have school today? Well, not necessarily, because the first thing is false. We're not sure if we have school or not. Okay, where the law of syllogism is just a little bit different because we're going to have two conditional statements here. Okay, the first, something like if today is Monday, then we have school. And you could have another statement like if we have school, then we have a hot lunch. So can you make a conclusion that if today is Monday, we're going to have a hot lunch? Well, it makes sense that it follows. If we have school, then this is true. If that's true, this part has to be true. And the law of detachment says if that part's true, R is true. So basically, we're skipping over the Q part, that we have school, and we're jumping right into the we have hot lunch. Okay, so we're simplifying these two statements into one statement. Okay, but they both have to be true conditional statements in order for that to work. I can get rid of that there. Okay, never mind. I'll have to fix that. All right, so inductive reasoning. Okay, I put this back in here because it's important. You want to know this. Inductive reasoning is based off of patterns. Okay, that's what the first thing we talked about in um, chapter 1. Deductive reasoning is based off of accepted statements, such as our postulates, theorems, definitions. Okay. Um, so we'll get a little practice of seeing which is which here. Is this inductive reasoning or deductive? Josh knows that Dell computers cost less than Apple computers. All other brands that Josh knows of cost less than Dell's. Josh reasons that Apple's cost more than all other computers. Okay, so Josh reasons that Apple costs more than all other computers. Did he do this off of accepted statements or looking at patterns? It looks to me like he did accepted statements, which would be your deductive reasoning. Now here, Josh knows that HP computers cost less than Dell computers. He also knows that Dell computers cost less than Apple's. Josh reasons that HP costs less than Apple's. Alright, so now I start to look at this and I say, did I get that first one right? They both kind of seem like deductive reasoning. Okay, so let me slow my thought process down. I'll get rid of this, okay? It's all right to make mistakes, but hopefully you catch yourself, and that's the goal. Okay, so let's look at this a little bit more. Josh knows that Dell computers cost less than Apple computers. All other brands that Josh knows of cost less than Dell's. Josh reasons that Apple's cost more than all other brands. I think the key here, all computers cost less than Apple's. All other computers brands that Josh knows of. Okay, so does he actually know for sure? No, he looks at a pattern that all other brands cost less than Dell that he sees. Okay, so it's not. This is kind of the key, that he doesn't know if he checked into all computers, but it seems like all of them are going to. So that should be inductive reasoning. Okay, we're down here. Josh knows HP computers cost less than Dell's. He knows Dell's cost less than Apple's. Josh reasons that HP costs less than Apple's. So he's not throwing in all other brands, something that he can't really check into. He's got his facts down that HP costs less than Dell's, Dell's costs less than Apple's, so HP costs less than Apple's. That's that law of syllogism in work there. So this would be deductive reasoning. Okay, last example. State whether the argument is valid. So here let's read through it and see if I can get it right on the first time this time. Michael knows that if he does not do his chores in the morning, he will not be allowed to play video games later in the same day. Michael does not play video games on Friday afternoon. So Michael did not do his chores on Friday morning. Is that a valid argument? Did Michael not do his chores? So we're that first if statement. Okay, it's not exactly an if-then form, but if he does not do his chores, then he will not be allowed to play video games. So if he does not do his chores, he can't play his video game. Okay, doesn't do his chores, doesn't play video game. Down here we say, well, he doesn't play his video game. So we know this part is true. Can we conclude that way? Well, is this a biconditional statement? It's not a biconditional statement, so this is invalid. We want more evidence. He might have just not wanted to play on that Friday afternoon. He might have had something else going on, right? Doesn't mean he didn't do his chores. And the last one, if two angles are vertical, okay, so remember vertical angles are these kind of angles, okay, then they are congruent. That is a true geometric property that we've talked about before. Angle ABC and angle DBE are vertical. So does that satisfy this first condition? It sure does. So then angle ABC and angle DBE are congruent, that is what you can conclude. So this is a true statement. The first part was true. That means, yes, the second part was true. So this is a valid statement. And is that the law of detachment or syllogism? That's the law of detachment. Okay. Got a law of detachment. They didn't ask for the actual reason, but might as well say it. There's your homework assignment for 2.3. You should have all day to work on that, so hopefully if you have questions over this lecture, you can either stop, rewind, or have some questions for me tomorrow in class. Have a good night.